Hi, my name is Okoye Celestine. In our previous classes, we looked at Heisenberg uncertainty principle and wave-particle duality. The Debroglie wave is a continuation of wave-particle duality, where we proved that waves behave like particles and particles behave like waves. Now, Debroglie, a French physicist, looked extensively at wave particles. He went on to relate the wavelength of a wave particle and its momentum, especially electrons and electron volts. We are going to look at some of the equations he propounded, which you can use to determine some parameters, while some other parameters are provided. Let's go on. The outline for today's class will just be introduction to the Debroglie waves, the mathematical expressions, we're going to prove them, and some solved problems and possibly assignments. Louis de Broglie in 1924 propounded this concept, which we also call the de Broglie hypothesis. Of course, we know that in one instance waves behave like particles, in another instance particles behave like waves. This means that matter appears to have dual nature. Mathematical expressions. Now, according to de Broglie, the wavelength of a particle is inversely proportional to the momentum. We understand what we mean by saying that wavelength is inversely proportional to momentum, which means that whatever happens to the wavelength has an effect on the momentum. Now, looking at equation 1 here, you see that wavelength is inversely proportional to momentum, P stands for momentum. Then, now if we look at this, you remember that once you remove sign of proportionality, a constant comes in. That is where we now have h, which stands for Planck's constant. So we have lambda equals to h over p. Now remember that momentum is always equal to mass times velocity, mv. So if we bring that back into the equation here, we have here in equation 4 that lambda is equal to h over mv. Thus, making mass times velocity, which is the momentum, so out of the formula here, we have that mv equals to h over lambda, which we have called equation 5. Now on this side here, we have the meaning of all the symbols, where lambda represents wavelength measured in meters, p represents momentum measured in kilogram meter per second, v, small letter v, represents velocity meters per second, capital letter V represents the voltage, which is measured in volts, then h represents Planck's constant in joule second, and E represents the electronic charge. Okay, as we go on, I would like you to understand that we have used V as capital letter, also as small letter, but they have different meanings, as I have indicated here. Small letter V for velocity, capital letter V for voltage. Now let us look at electron volt. In one of our classes, we looked at electron volt, where we said that electron volt is the energy acquired by an electron when it is made to pass through a potential difference of 1 volt. When a PD of 1 volt passes through an electron, that electron acquires energy, kinetic energy that it's used to move. Now let's look at this other bullet here. An electron of mass ME with accelerating voltage V has kinetic energy equals half mv squared and momentum equals P equals mv. Now this means that once an electron acquires energy after passing through a potential difference of 1 volt, it can move, and the EV represents electron volts, which is the energy acquired, and that energy acquired must be equal to the kinetic energy it is moving with. Thus we have that EV is equal to half mv squared, showing that electron volt is equal to kinetic energy the electron is moving with. Now if we look at this further, you see that EV being equal to 1 over 2 mv squared. Now if we make mv the subject of the formula, let's follow the bullets we have here. Let's make mv from the equation above, subject of the formula, and combine it with the Debroglie equation. At the end, we are going to see what we have. From the above equation, we have what? That 2EV equal to mv squared. Now from this equation here, what we'll do first of all is to cross multiply. If we cross multiply, we have that 2EV will be equal to what's left, mv squared. So from that, we divide both sides by what? Small letter v, which is the velocity. We're going to have 2EV over v equal to mv square over v. V will cancel one of the v's up here. Thus we have what? 2ev over v equal to what? mv. Let us call that equation 7. Now let us put mv equals h over lambda into this equation. Now if we remember mv, this equation here, equation 5 here, let us bring it back into this. Let us bring it back here. mv equals h over lambda. Let us put it into this equation 7 here, which means we are here where we have mv. We remove this mv and put what? H over lambda. Thus, we are going to have what? 2ev over v equals h over lambda. From here, if we cross multiply, we have that 2 lambda ev equal to what? hv. So if you cross multiply from here, this multiplies this, while this multiplies this, we have this here. Now let's divide both sides by 2ev. If we divide both sides by 2ev, you see that 2ev down here, we cancel 2ev equal to hv over 2ev. So this will cancel. We have left, we have lambda equal to hv over 2ev left. We have called that equation 7. Now from electron volt equation, which equals kinetic energy, if we make v, this velocity here, subject of the formula, thus so that we can be able to determine the velocity of a wave particle, what we need to do here is simple. First of all, you just cross multiply. If you cross multiply, we have 2av equals mv squared. Then you take what? The square root of v. Look at the process here. We'll explain the process here briefly. So we have what left? V equals square root of what? 2ev all over what? M. We have called that equation 9. Now let us put equation 9, this, into the basic equation of momentum, P equal to mv, which means as we have P equal to mv, here we have V. We are going to remove this V here, and we bring in this, what V represents here, 2ev over m, all square root. So if we put that here, we have that P equals m into square root of 2ev over m. We have called that what now? Equation 10. Now let's go further with balancing and making this equation seem normal. Let's take m into the equation. This m out here, we take it into the square root. So we have what here? P equals all squared 2ev m squared all over m. You know, if this m now, this square now, we cancel this square, which can bring this one out. So if we have that, we go on to cancel m. Because m down here, we cancel one of the m's up here. We have what left? P equal to 2evm. Now, let us put this equation 11. Equation 11 here. Let us put equation 11 into lambda equals h over p. Of course, we know this equation as one of the first equations De-Broglie propounded, which means lambda equal to h over, instead of putting p here, we bring what? Square root of 2ev and put here. So we have that lambda equal to h here over, instead of writing p here now, we have what p represents, which is equation 11, we bring it here. So we have lambda equals h over 2evm. Remember that all the symbols remains the same. Their usual meaning: lambda wavelength, p momentum, small letter v velocity, capital letter V voltage, h Planck's constant, e electron charge. Now with these equations, we can determine the wavelength, momentum and velocity of a wave particle. These are some of the equations. These are the equations we derived just now. Lambda equals h over p momentum, lambda equals h over mv, lambda equals hv over 2ev, ev equals half mv squared, p, which is momentum, equals square root of 2evm. Then lastly, lambda equals h over square root of 2evm. Now with all these equations, you must make sure you know these equations, because they will help you to solve problems under wave particles, especially regarding to De-Broglie waves. Let's look at some solved problems. Calculate the wavelength of an electron of mass 9.1 times 10 to the power minus 31 kilogram moving with a velocity of 2.0 times 10 to the power 6 meters per second. In the bracket, we are provided with Planck's constant 6.63 times 10 to the power minus 34 joules second. Now, from the Debroglie equation, we have that lambda equals h over mv, which I think is the best equation to solve this problem with. So what we need to do is just bring in the parameters that are provided. H here is equal to Planck's constant, which we have put here, 6.63 times 10 to the power minus 34, all over mass, which is 9.1 times 10 to the power minus 31 times velocity, which is 2.0 times 10 to the power 6. So if we do all this mathematical, if we solve this, we have what, 3.64 times 10 to the power minus 10 meters. Of course, you know wavelength is measured in meters, so we have 3.6 times 10 to the power minus 10 meters as the wavelength of the electron. Second question, let's look at this. If electrons are accelerated from rest through a potential difference of 10 kilovolts, what is the wavelength of the accelerated electron? So we have all the parameters here. ME standing for mass of electron, which is equal to 9.1 times 10 to the power minus 31 kg. E represents electron charge, 1.6 times 10 to the power minus 19 coulomb. H, which represents 6.6 times 10 to the power minus 34 joules second. Now, the first thing we are supposed to do is to convert 10 kilovolts to volts. You remember that kilo represents 1000, so this is going to be 10 times 1000 volts, which will give us 10,000 volts. So we are provided with the right parameters, so the best equation to use is this here, where we have lambda equal to h over square root of 2 EVN. Why? Because if you look at the parameters, all of these are provided. So I think that is the best we use. So if we put all the parameters right, we're going to get our final answer as 1.22 times 10 to the power minus 11 meters. Wavelength is still measured in meters. Please be careful how you calculate. Make sure you follow the right steps. Jumping any step may lead to error. Okay, we have another question here. Calculate the minimum wavelength of X-ray when a wavelength of 60 kilovolts, remember we'll convert 60 kilovolt to volt, when a voltage of 60 kilovolt is applied to an X-ray tube. We have the parameters provided. Speed of the wave C, which is C, equals 3 times 10 to the power 8 meters per second. Electronic charge 1.6 times 10 to the power minus 19, then H, Planck's constant 6.6 times 10 to the power minus 34 joules second. So the solution, we first of all convert 60 kilovolts to volts, which will give us 60,000 volts, because we're multiplying 60 times 1000. So if we do that, we have this equation here as the best equation to use, because we are provided with H, V, E, and capital letter V, which is voltage. So we put all the parameters, all the values right, we are going to get our final answer wavelength to be equal to 1.03 times 10 to the power minus 11 meters. Thank you so much. I hope you understand this. If you have problems or you have questions, drop your comments or chat me up on the number provided there. Don't forget to subscribe to our YouTube channel for more videos. Thank you. My name is Okoye Celeste.